So in this segment, we'll give you a very crude introduction to statistics just to illustrate some concepts. Again, we're compressing material that will be taught over multiple semesters just as a way to fill in some background to help software engineers understand how the role of statistics plays in the validation of software. So what are statistics? A statistic is just a measure. It's really a number extracted from a data set. That's all there is to it, really. The appropriateness of that measure depends on the application. So the most common ones you may have heard of are the mean, the average number, the average value of some data set, the median, the central value, the mode, perhaps the most common value you will see in a data set. And the goal of statistics is to learn something from a sample to draw conclusions about the population as a whole. So just to re-emphasize this thing, we want to learn something about the population. Does this drug work on the population as a whole? The population are all the people who might be part of what we're trying to do. So if we have a drug for kids with a particular disease, the population are all the kids that have that disease. The sample is a group of kids that we will actually study. We can't study every single child that has that disease. And our goal is to extract some information from that sample to draw conclusions about the population as a whole. Because while we're interested in the children that are in our sample, really they're a small group. What we want to do is to extract information that generalizes to the population as a whole. And this is the key, this concept of generalization. So let's give you some example of statistics. Let's go for a very silly example. Example 1, how much pizza do we want to order? We're ordering pizza for a group, and the appropriate statistic here is the average number of slices per person. Again, assume there's only one kind of pizza here. Given the average and the number of people, we multiply, we figure out how many pizzas we need, and we go ahead and order. So here's a situation where the appropriate statistic is the mean, it's the average. That's all we really need to know. Let's take a second example. And this is where we get into earthquake-safe construction. And the goal here is to figure out how strong a building needs to be to survive an adverse event, an earthquake. The average strength of past earthquakes is of no use. We don't really care about the average. What we really want to know is what's the strongest earthquake reported in the past however many years. And this is the maximum of our sample. And in true engineering function, we'll then add 10 to 20%, 50%, 100% over and above that as a safety factor. So that's important. When people think of statistics, they always think about the mean. What is the average value? They think that that is representative. And the mean sometimes is in fact representative. But sometimes there are other things that are representative. What we may want in the case of earthquake construction is the maximum. What is the highest value earthquake we're going to see? Because that's what you need to design buildings. In fact, if you think what the average value of an earthquake in any given day is in most places, is in fact 0. Right? But you don't design buildings for 0 earthquakes because eventually you will get one. What you want is to design based on what's the strongest earthquake likely to be in the next however many years. So this leads us to a process of statistical estimation, this concept of estimating values. We use measurements from a data set, a representative sample, as we discussed before, to make inferences, educated guesses about the population as a whole, because we can't really measure everybody. The example here is we estimate the typical time our software takes to do something, okay? The population here is every instance at which our software is going to run. The sample is the number of measurements we make. The process might be run the software multiple times, these are the trials or samples, on the typical hardware and measure the time, compute the sample mean, the average time it takes for task over the trials, and use the sample mean as an estimate for the population mean, the mean of all possible runs. So if we assume that our sample is representative, the average of the sample should be close to the average of the population, provided our sample is large enough. And this is the core of statistical estimation. Things get complicated really fast, though, okay? So there's more to statistics than that. There's a reason we pay statisticians good salaries. We want to know, for example, here, how likely is that the task takes less than 2 seconds? So we want to, effectively what we're going to do here is we're going to estimate the probability density function for our measurements. And we'll talk a lot more about this process in the next one. Once we have this, we want to compute the cumulative density function for a value of less than 10 seconds. So remember, this is the probability density function. The cumulative function is just the area under the curve summed up below the value of 2 seconds, which could be right here. So if we say this is in fact 2, all these events here are less than 2. This is more efficient than compared to running an algorithm multiple times and then computing the fraction of times that the algorithm took less than 2 seconds, right? It's more efficient, it turns out, mathematically. If we have a model, we can use it to extract information. And this is a fundamental truth in all statistics. Given enough data, the problem is often easy. The hard task is to be able to say something useful given a limited amount of data. And you see that, for example, in opinion polling. If you ask 1,000 people and you try to predict what the outcome of an election is, it takes a lot of skill to balance that sample, to figure out you're getting all the right people and not too many of one kind of person to say something interesting about that. If, on the other hand, you could ask every single person in a country what they're likely to vote, then it doesn't take any skill anymore. Chances are the average you get will be the true result. There are two kinds of estimation. We have point estimation, where we're interested in estimating a single number. So this is the best guess of what the actual parameter in the population might be. What is the average wealth in this group? What's the average height in this group? And then we have interval estimation. We get two numbers called the lower and the upper bound for a specific parameter. And this is often known as the confidence interval, and it's associated often with a confidence level. For example, 95% of that parameter is within the bound. So if we take height, for example, we could estimate the average height, and it could be 1.75 meters, or we could be interested in what are the bounds with which 95% of all people lie. And it might be between 1.5 and 2 meters. We know that 95% of all people will be in that range. I'm probably being a little conservative here. To conclude this segment, we'll look at two important elements that undergird a lot of statistical theory, and these are often ignored or forgotten, that these fundamental constraints are there. And when they are violated, we often get into trouble. So let's talk about them first. All of the statistical techniques rely on these fundamental results. The first one is what's called the Central Limit Theorem. And what this says is that under certain conditions, the sum of lots of random variables has a normal distribution. So you start with some coin or some dice, you roll it, you get value 1 to 6, that's not normal. But if you keep doing it and you keep adding values, what this says is that provided some conditions are met, and these are fairly general, you get a normal distribution. So let's look at this in action from a simulation I ran. This is one die, uniform distribution, 1/6 here. Every single value is 1/6. Once we do two die, remember the sum from a couple of segments ago, we get this triangular shape with the high value being at 7, because that's the most likely sum, the low value being 2 to 12, and you get this triangular thing. If you keep going, you do 5 dice, you get this peak thing. Once you get to 20 dice, this is now beginning to look like a Gaussian, a normal distribution. And this makes life very easy when it's true, because if we're trying to estimate the average of some parameter in a population, if our population is big enough, we can make the assumption that it's likely to be a normal distribution. And then there's lots and lots of machinery we can use to make our life simpler. Normal distributions are really nice to work with mathematically. The second key element is what's called the law of large numbers. And what this says is that under certain conditions, the estimates of parameters, for example, the mean, converges to the true value. And this is true, but let me give you in many cases when the values are bounded and there's some technical condition. But let me give you a counter example here, which is the billionaire example. Let's first of all start with something that is true. This is the average estimate of the height over people. So we take a first person randomly, they have a height up here, and then we take a second person, now we update the average, maybe they're a little taller, a little shorter, and this goes up and down, and we hopefully end up with something that's close to the true mean of 1.75 centimeters. If, on the other hand, we're interested in measuring wealth, the average wealth of people, and let's say we are unlucky in our measurement, or very lucky, depending on what you're trying to do, and the first person is a multi-billionaire. Now the average, our first estimate of the average is 10 billion. It would take a very large sample before that value goes down. So let's say the second person is penniless, we end up with 5 billion. The third person is penniless, we're now into 3 billion. But by the time you get to something that approaches the true value of the average wealth, you need a huge sample. So here's a case where the law of large numbers is violated. And so fundamentally, we assume in most analysis in statistics that those two things are correct. We can use the central limit theorem. We assume that if we have a large enough sample, our estimates will converge to the actual value of the sample. When these things are true, life is easy and all of the statistical machinery works. When these things fail us for whatever reason, we have unbounded values, there's no upper bound to wealth really, or they have values very far away from the mean, then sometimes we see interesting, weird results. And if you make too strong of an assumption about the wealth has its way of getting at you as well. So examples of this come with the failure of many models to predict stock market values in the 2007 crash, where they made the wrong assumptions, and a lot of them were hurt severely by those mistakes. So this concludes this initial foray into statistics. In the next segment, we'll zoom in and take a look at the problem of estimating probability density function, which is one of the key processes that we will use in clinical trials and things like that. Thank you.